Topic introduces machine learning methods and their growing importance in financial analysis and risk management. Machine learning refers to computational techniques that identify patterns in data and improve predictive performance through experience, rather than explicit programming. The program explains that machine learning has become increasingly valuable due to the expansion of financial data, advances in computing power, and the need for more sophisticated analytical models. In finance, machine learning supports fraud detection, credit scoring, portfolio optimization, algorithmic trading, and risk forecasting. These techniques allow analysts to uncover complex nonlinear relationships that traditional statistical methods may fail to capture effectively. A major focus of the topic is the distinction between supervised, unsupervised, and reinforcement learning models. Supervised learning uses labeled datasets to train models that predict outcomes such as default probabilities or market movements. Unsupervised learning identifies patterns or structures within unlabeled data, making it useful for clustering and anomaly detection. Reinforcement learning differs by allowing models to learn optimal actions through repeated interaction with an environment and feedback mechanisms. The program emphasizes that each approach serves different financial objectives depending on the availability of data and the nature of the decision-making problem. Understanding these categories helps analysts choose appropriate machine learning methods for specific financial applications. The topic also discusses the importance of data preparation in machine learning workflows. Financial data often contain missing observations, outliers, inconsistent formats, and irrelevant variables that can reduce model accuracy if not handled properly. The program explains that pre-processing techniques such as normalization, standardization, feature selection, and dimensionality reduction are essential for improving model performance. Analysts must also divide data into training and testing samples to evaluate predictive accuracy objectively. Effective data preparation helps prevent overfitting, where a model performs well on historical data but poorly on new observations. In financial risk management, robust data handling procedures are critical because inaccurate predictions may lead to flawed investment and regulatory decisions. Another major topic is principal components analysis, PCA, an unsupervised learning technique used for dimensionality reduction. PCA transforms correlated variables into a smaller set of uncorrelated components that capture most of the variation in the original data. The program highlights that PCA is particularly useful in finance because markets often involve large numbers of correlated risk factors. By reducing dimensionality, analysts can simplify models while preserving essential information. Applications include interest rate modeling, portfolio risk analysis, and factor-based investing. PCA improves computational efficiency and enhances interpretability, making it an important quantitative tool for managing complex financial datasets and identifying underlying market drivers. The program also introduces clustering methods, particularly k-means clustering, which groups observations into clusters based on similarity. K-means algorithms partition data into a specified number of groups by minimizing within-cluster variation. In finance, clustering techniques are used to classify borrowers, segment customers, identify trading patterns, and group securities with similar characteristics. The program explains that unsupervised clustering can reveal hidden structures within financial datasets that may not be immediately visible through traditional analysis. However, analysts must carefully select the number of clusters and interpret results cautiously because clustering outcomes can be sensitive to initialization choices and data characteristics. Natural language processing, NLP, is another important machine learning application covered in the topic. NLP enables computers to analyze and interpret human language data, including news articles, earnings reports, social media posts, and regulatory filings. The program explains that financial institutions increasingly use NLP to extract sentiment, detect emerging risks, and improve forecasting models. By converting textual information into quantitative signals, analysts can incorporate broader information sources into investment and risk management processes. NLP techniques are particularly valuable because financial markets react rapidly to information flow. The ability to process large volumes of textual data efficiently provides firms with potential competitive advantages in forecasting and strategic decision-making. The topic further examines reinforcement learning, which models sequential decision-making processes through rewards and penalties. Reinforcement learning algorithms learn optimal strategies by interacting with environments and updating decisions based on observed outcomes. The program discusses Q values, which measure the expected rewards associated with alternative actions. In finance, reinforcement learning has applications in algorithmic trading, portfolio rebalancing, and dynamic hedging strategies. These models are particularly useful in situations where decisions must adapt continuously to changing market conditions. However, reinforcement learning models can be computationally intensive and sensitive to the design of reward structures, requiring careful implementation and monitoring in real-world financial environments. Overall, topic demonstrates how machine learning methods are transforming quantitative finance and risk management. The program highlights that machine learning techniques provide powerful tools for prediction, classification, clustering, and pattern recognition in increasingly complex financial systems. At the same time, the topic stresses the importance of proper data preparation, model validation, and awareness of overfitting risks. Machine learning complements rather than replaces traditional financial theory by enabling analysts to process larger datasets and identify nonlinear relationships more effectively. By understanding machine learning methods, candidates develop advanced analytical capabilities that support innovation, improved forecasting, and more effective management of financial risks in data-driven markets.